Okay, hi everyone. Welcome back after lunch. I hope that was a nice wee break for you all. Um, let's get back to things then for this afternoon. Let's restart sharing my screen again. Where are we? There we are. Okay. Okay. So I said before lunch that we would just do this exercise. Take 10 minutes to do this after we get back from lunch. So just to finish off our section on arrays, we're going to do a little bit of work on allocatable array arguments. There are some things that we will spot doing this that are things to watch out for when you're working with allocatable arrays in this way. So we've got two sections here. The later ones are questions. So the first one is a coding exercise. So we've got to write a short example along the lines of example 2.f90 to check that an allocatable array, an allocatable dummy argument with intent out is actually deallocated on entry to the subroutine. So let's just take a quick look again at example 2.f90. We can see here what it looks like. We created our array. A, we said it had a size of 5, and we gave it 5 values, 1, 2, 3, 4, and 5 inside it. Then we called an array operation on it, and we did 1 to 5, the stride of 2, set those values equal to 0, then came back and printed it out. So we've got to write something along those lines to check that an allocatable dummy argument with intent out is indeed deallocated on entry to that. So I'll say that we should all do this together. I will start to write on screen the skeleton of what this code might look like, and you can follow on and then fill in the gaps yourselves as to try and see how this can be done. And we'll check what this looks like. So yes, so I do invite everyone to have a go at this at the same time. So let's just call it exercise 1 for the sake of it, .f90. Oh, I should say, by the way, you will see that for a lot of these directories, there is a solutions directory in there. So in here is a complete example solution that you can take a look at just in case you miss what I'm doing. You come back to it in the future and want to try again. So you can take a look at that at some point if you want. But for now, let's just start from scratch. Let's just do this. So we're going to write a program similar to example 1. So let's just call it exercise 1 as before. Because it's none, I'll put in straight away and then end program exercise 1. And inside it, let's create a real array. And remember, we want this to test. We want this to test an allocatable array. We want to see, is our allocatable array actually deallocated on entry to our subroutine? So let's just do this. Real allocatable array, and we'll say it's going to be a rank 1 array. We can then allocate it. So remember, we can do this a couple of ways. We could just do a equals and then give it the values that we want to give it: 1.0, 2.0, 3.0, 4.0, 5.0. Let's just do it this way for the sake of it. Remember, as we saw earlier on, this would not work. We have to actually say allocate A as a new region of memory and put these values into it, but we have to use A as a whole. We could, if we want, do allocate array, allocate A5 beforehand. Let's just leave this out so that we can at least use that new bit of syntax. So those are our initial values in it, just so that there's something. And then we'll call, we called it my array operation, didn't we? So let's call it my array operation, which is just going to take A as that's one argument. Again, if anyone has any questions during this, please do ask during while I'm doing this. And And now we'll put a subroutine in here alongside it. Let's just call it subroutine my array operation again, just as we had in the example. And we'll just call this, we'll call it array, just to make clear that it's something different. And I need to change my default indentation on this this account. And remember, we were testing what happens when it has intent out. So I'll give people just a minute to work out what they might do from here. I'll leave it there. So what we're looking to do is to find the allocation status of array. So I'll give just a minute for people to maybe see what they want to do here. Okay, I don't think a lot of time is needed for this. So something we could do really simply would just be, for example, right here to do print star allocation status of array, and then just do allocated array. So this is really simple. That we can do a little bit more than this, but as a starting point, oops, my array, of course, I'm getting ahead of myself. End subroutine, my array operation. Okay. Oops. Okay. Array state allocation status of array is F. So we can see really when we, although here it was allocated. In fact, let's just put another one in here to be really clear about things. Print star allocation status of A is allocated A. Let's just compile that and run that. So when we were out in the main program, the array was indeed allocated. When we went into the subroutine, it became deallocated. So because we said it's intent out, what we're saying here to the compiler is we really do not care what array was before we entered the procedure. It's actually taking that to be an even stronger statement and saying, and the compiler is going, okay, in that case, I will deallocate it at the point of entry, and it's then a completely blank slate ready for whatever code we put here to work with. What if we then, we could then do whatever we wanted to it. We could change. We could change it. Let's see. So we can now say array equals, let's say 10.0, 11.0, 12.0, for example. And then let's just do print star allocated again, just to show what's happening. It becomes allocated once more. Oops. It did not let me do array brackets colon bracket equals 90. No, it wouldn't do. So remember, there is here a very important difference. So either here or up here, in either place, if we did this, that wouldn't work, because at this point the array isn't allocated. And when we put bracket colon bracket, what we're saying is put this value or these values into all of the entries of A, and they don't actually exist yet. Yeah, I think you've just realized it too. Yep. So we need to specifically say array or A as a whole. So this is now saying allocate array and put these values into it. When we do this, all we're saying, oops, when we put bracket colon bracket, we're just saying put these values into it. We aren't including the allocate it and then put the values in. Okay, I hope that makes sense to everyone. I hope you've all been doing that at the same time. It's not a huge exercise, it's just a nice little thing to try out. We can take that a little bit further. Can an array section be passed to a subroutine where the corresponding dummy argument has been declared allocatable? Well, why not give it a go? Let's call my array operation on colon 2, which we've done a few times. Basically saying, take all of the odd elements of A and pass those through. What happens if people try this? If anyone wants to give it a go and put in the chat what they find, we can change this too. Let's for the sake of it, let's make this intent in out. Anyone want to have a go at passing the slice through? Dummy argument A has the allocatable attribute. It requires an actual argument with the allocatable attribute. Okay. Do I get the same? Yes, I do. So this is actually not a very helpful error message. Let me just actually, out of interest, let's try again. So this is again the Cray compiler. Let's see if G Fortran gives a more helpful error message. No, it doesn't. So it is correct, but I'd say this isn't, in this case, entirely helpful. So yeah, so you've got the exact right thing there, Ewan. But what's actually happening here? Take a look. Is what we're saying is we're going to pass through a slice, a section of A, all of the odd elements only, and we're passing that through as an allocatable array. Because we've now said that this is in out, but it would be just the same as if we had in out. What we're now saying is that the allocation status of the array of the dummy in here can change, corresponding to the actual arguments up here. So, for example, what we could do, let's just keep it as in out for the sake of it, is we could do in here deallocate A, allocate A, whatever, just making things up, 10, for example. What does that mean when we have a section up here? It means basically that these two things are not actually compatible with one another. If we're saying that because this is allocatable, we are allowed to deallocate. Oh yes, you're right. This should be array. Yes, good point. Array. Keep the dummy name correct. Yes. Because inside the array, because it's intent in out, we can change the allocation statement. So whatever array is, we can release it back into the heap as free memory, and then we can create a new allocation in the heap memory and say array now points to that. But up here, our actual argument is just a section of A. So would we be able to deallocate just the odd components of A? No, we wouldn't. We couldn't reallocate those to something else. It doesn't make any sense. So what the compiler is actually in a very roundabout way saying is that if you want to pass a section through here, it cannot be allocatable here. What you could do is you could make everything here not assume it's allocatable. You could do something like this. Of course, then allocated wouldn't mean anything. I think this should work. If I then print out, let's just print out A up here as well. Coding very, very quickly. So you can see we've now changed those entries. So that's fine now. The issue was that it was allocatable here, and that means that the allocation status can change, and we cannot change the allocation status of a section. That was the issue. Okay. One last question here. What happens if the function with an allocatable result returns with the result in an unallocated state? Very simply, I don't think I even need to bother showing this. The variable assignment itself is going to be unallocated. Really, you should try and not do this. Okay, so I think probably actually this last little bit here, these two exercises, I think were hopefully fairly instructive, and some of the slight gotchas that can catch people out when they're working with allocatable arrays in particular as dummy arguments. So our next section, which I'll move on to now, is going to be pointers. But before I do that, here's a chance to ask any questions if anyone has any about anything that we saw just then. Okay, I think that's a go from everyone. Okay, in which case let's carry on. Okay, so pointers, yes, I think people in general are a little less experienced with pointers because they are comparatively new in Fortran, and because arrays are so nice in Fortran, I think people in general have just fewer opportunities to work with them. So let's go through a very brief refresher on pointers. Yes, it's worth just pointing out again that pointers in Fortran are like arrays, a bit more complex than pointers in, say, C, for example. In C in particular, where pointers, if you're used to C, pointers are a very low level way of accessing raw memory potentially. They're very helpful, particularly in things like systems coding. C++ also gives you some more advanced types. Unique pointers, very helpful. Fortran is a little closer, I guess, to C++ here, in that pointers are actual objects again. Like arrays, pointers have metadata that comes along for the ride and helps the compiler and the runtime work with them, perhaps a little more safely, say, than bare pointers in C. So remember, to create a pointer to any given type, we just add the attribute pointer. So integer comma pointer says, give me a pointer to an integer type, and here we're going to call it p1. we create another couple P2 and P3. They're all integers to pointers. And then with the special arrow operator equals arrow, we then get to associate it to something else, some target. We'll talk a little about that in just a second. If you create a pointer, it's best practice by a massive way to make sure that it's associated with something from the very beginning. So either with null, which means it's not pointing to anything at all, or to some target t. What you should try to never ever do is just leave it undefined. So if you don't point it to anything, it stays undefined. But then what you can't do is you can't check it with the associated intrinsic function. If you use associated, you can either get false if it's pointing to null, or true if it's actually pointing to something. If it's undefined, then whatever this does is also undefined. So you really do want to make sure it's always pointing to either null or something real. And yes, whatever your pointer is and whatever your target is pointing to is, they need to match in type parameters, and the rank of both. So that means, you know, if your target is an array, then you need your pointer to be to an array type as well. That's a big thing to watch out for. An example here, and that is, this is of an array. Let's say that we have A, and we give it the target attribute, just comma target tacked onto the end there, and that's now says to the compiler that A should be available for pointers to point to. And then we say that P is a pointer to a rank 1 integer array. So there is a little bit of syntax here. This is another tiny gotcha, in that this does, if you look at it, also look like it could be not a pointer, but an array of pointers, and it isn't. This is a pointer to an array, and specifically a rank 1 array. So this can be a little bit strange if you're looking at this for the first time and you aren't used to it. There's a trick that you have to use if you want an actual array of pointers. So just bear in mind, if you see either just brackets and colons here in your pointer, or if you put a dimension in here with the same some specification of how many ranks there are using colons, it isn't an array of pointers. It is a pointer to an array of whatever rank and whatever kind. So in this case, we have a rank 1 array of integers, which are a target and a pointer to an integer rank 1 array. And so we can just say that P now is going to point, and here we've been a little bit clever too. We've said that P isn't just pointing to the array A, but it's also pointing to an array section. So it's again pointing to all of the odd elements of A. So the shape and the bounds have to be what are on the right hand side. So this here says that's what we're going to get. So what you can now do is you can also use things like shape, L bound, and U bound on your pointer directly and find out what it's talking about. And again, you can also say that the indices are going to have some different lower bounds, and you can also even reshape multi-dimensional arrays. What you do have to do when you do this is you have to be a little bit careful, because first of all, you have to make sure that your multi-dimensional pointer is only reshaping target arrays of a lower rank. That does make sense if you think about it. Going the other way around doesn't actually make any sense. And you also have to make sure that the sizes are able to match. So if you ended up, say, setting up your pointer so that its size was greater than what's in your right-hand side target, you would, I think, in that case, always get a compiler error, unless, of course, it has no way of knowing what size of the what the size of the target array is. That would be an error. It would say your pointer, as you're setting it up as an array, is bigger than what it's actually pointing at. It's able to spot that if that happens. What you might also do, it doesn't say here, but you might also just choose to use a Fortran associate block to do this instead. That might be a slightly easier, perhaps slightly safer way of doing that, but pointers are perfectly valid as well. It's worth noting, yes, if the target of an assignment is a pointer, then any changes after that in the status of the target aren't reflected in any later assignment. So if you basically chain pointers pointing to one another, because remember, pointers can also point to pointers. So we could have, say, an original target A that we then point B at, and then we point C at the pointer B. So what we've now got is B pointing to A and C also pointing to A. That's something that is hidden away here. It looks like C is pointing to B, but via B, it's actually now pointing to A. If you did this and then you said nullify B, and that sets B pointing to null, C is still pointing to A. And you can't see that. So this is why pointers are a little, just a tiny little bit dangerous, because you can't necessarily see that stated explicitly in the code. A question: was B declared as a target for C? No. So here we would have said that A is a target. B was a pointer, and C was a pointer, because pointers can point to pointers or targets. Something again, a little something just to remember: pointers can point to pointers, and in that case, what you actually point at is not the pointer, but whatever that pointer is itself pointing at. So you've got multiple levels potentially of indirection here. Fortran isn't like C, where when we work with pointers, we are working with the actual locations in memory, the addresses. It sort of handles all that for us in the background. We don't have to think about indirection and referencing. We just tell Fortran what we want it to point at, and then we work with it as if we were working with the original target. So when we do C points to B, and then we start working with C, we're just working directly with A under a different name, C. Then if we say, okay, B is now null, it doesn't matter. C is still pointing to A, because at the point where we did C points to B, B was pointing to A. So we just go C points to A. Whatever happens to B afterwards just doesn't matter. Just to briefly mention that nullify statement, it's just the same thing as doing something pointing to null, just the same thing, except that if we do that, then nullify can take a comma separated list of multiple pointers that we want to set to null. So it could just be a quicker way of doing it rather than saying p1 points to null, p2 points to null, p3 points to null. Well, instead of that, just do nullify p1, p2, p3. Something that is also important, again, pointers can be a little risky in some ways, because again, yeah, any time that we start working with memory, we get little bits of risk introduced. Is that if we had a pointer of whatever type, we can then allocate that pointer. Hopefully everyone here knows this. But if you allocate the pointer, then what we're doing is we're creating memory for it on the heap, and then having our pointer point to it. If you've done that and then you nullify it, whichever way, either by using the statement or pointing it at null, you aren't deallocating that memory. You're still leaving it there. You're just saying that the pointer which was pointing to it now isn't anymore. It's now just pointing at null. So that's something else to remember. You would want to still deallocate that before you do anything else to make sure you don't lose track of where that memory is. So we have a brief exercise here. We've got a bare outline in example 1.f90, and this is now in the O2 O3 directory. And we've got to write a program which initializes an integer array, A10, assigns the elements the values from 1 to 10, and then we're going to create a pointer which points to the even numbered elements of A2 to 10, just as we did just above here somewhere. Where was it? Just here. Print out the values returned by the functions. So we've got to print out L-bound, U-bound, and size when we apply to the pointer, and then check that the value associated with that is 8. So let's just take a few minutes, five minutes it says here. We may not even need that. This should be hopefully fairly simple. Starting from example 1, let's just take a quick look at that. So let's go into the O3 more on pointers directory. Again, this is more on pointers because this is following on. This is the assumption here is that everyone is up to date with pointers, at least as far as the introductory course on Fortran goes. So let's take a look at example 1.f90, and here's our bare program waiting for us to do what we were told. So let's create that array, put the numbers into it, set up a pointer pointing to it, and then just check what do these give when we start using the pointer with them. So I'll give everyone just a few minutes there, and then we'll take a look and see what we get. Okay, I'm going to just start entering little pieces of the start of the code. So if anyone's just struggling to get going, you can hopefully see how I'm getting it all started, and you can build on that. Okay, I've done quite a lot here. The only bits I've left for you to work out are how to do this pointing, and then printing out the upper bound and checking the size and elements of the pointer P as well. Just give everyone one more minute for that, and then we'll take a look. Okay, I hope everyone's been able to do this. So let's start up here by pointing P at the correct elements of A. So let's say that A has to look something like this. So we said we want it to be all of the odd elements. That means that we want to have our section start at 2 and run up to 10 with a stride of 2 elements. So we want elements 2, 4, 6, 8, 10. And we just do it pretty simply, just like that. So now P should just be pointing at those. Then the only other things we have left to do, I have to print out what the upper bound is. We'll just do this the same way, U bound P. And let's also print out its size. Just use the size intrinsic on P, and also the fourth element, wasn't it? So let's also print out P4. And assuming I've not missed anything silly, that will hopefully compile. And hopefully it's correct beyond just compiling. Okay, here we go. So we can see that we've basically got an alias now. Our lower bound of P is 1, our upper bound of P is 5, size of P is 5, and P4 was 8 as we were expecting to find. So when we do this, when we do this this aliasing, it's sort of the same kind of shift in indices that we saw when we passed arrays through to procedures. Whatever the indexing was before, after we do this, P is now saying that element 2 of A becomes element 1 of P, element 4 of A becomes element 2 of P, and so on, up to element 10 of A. So A10 is mapped to P5. And as we would expect, the size of that was also 5. P4 came out as element as value 8. We could change this. We could have just printed out print star. Let's just print P for the sake of it, the entire thing. 2, 4, 6, 8, 10 is what has come through from that. Okay, I hope that wasn't too tricky for anyone. Please shout if you have any questions. Is there anything in here? No, just the example code. So for a lot of these, if you click show me the solution, it will show what a solution code will look like. Again, that's probably there in the solutions directory as well. Oops, example 1. Yes, broadly the same as what we did just now. Okay, I can't see any questions in the chat, so let's move on to think about pointers as arguments. So our dummies that are dummy arguments when we're writing our procedures can also be pointers. If they have intent in out or intent out, then it also must be a pointer. If it's intent in, it's fine. It would just treat the pointer on the outside as being a reference again to whatever the original target is. It's only if you're expecting your procedure to change it in any way, either with in out or out as its intent, but you have to say, yes, we do have to be pointers everywhere. So the pointer actual argument can correspond to a non-pointed dummy. Yeah. Oh, but this is yes, what I was just saying. Yes, it can just be associated with a suitable target. There are some oddnesses yet again here to be aware of. So when you provide arguments, they have to they should really point to different things. So what you should really be trying to do, because with pointers we're working with locations in memory much more closely, if you aren't careful and end up with multiple arguments pointing to the same chunk of memory, you can end up with code that has effects you probably aren't intending for. Bugs, basically, you can introduce bugs in that way. So if you're coming from C, you might know about using restricts on your dummy arguments, where you're basically saying to the compiler, don't worry about it, I'm absolutely certain these will not be the same location in memory. They aren't aliases to one another, and you can perform some extra optimizations to hopefully improve the performance of this code. In Fortran, that's a little bit different, because remember, we're doing something that might be passed by reference, but can also be copy in, copy out. We are never really sure unless we compile code and then go and take a look at the assembly that that the compiler generated for us. And that means that this is actually a little bit more complex, actually. So there are some things to think about here. We've got two examples, I believe, here to look at. Let's imagine that we have a subroutine like this. My array update takes two integer arrays, both intent in out. And let's say that IA, the first array, we're going to take all of it and add 1 to whatever was in there. Then we've got another integer array, our second dummy argument, IB, and we said whatever's in there, divide it by 2. But now you can imagine that we've made an argument like, we've made a call, sorry, like this. My array update A 1 to 10 and A 6 to 15. So even though we aren't working with pointers, because we're talking about chunks of memory and we're using the same thing here for both of them, we potentially run into issues here, because now we've got the same memory on both of these. But as far as the function here, sorry, the subroutine here is concerned, they are different things. It says whatever IA is, we're going to add 1 to it. Whatever IB is, we're going to divide it by 2. But now we've got A 1 to 10 and A 6 to 15. So both IA and IB contain elements 6, 7, 8, 9, and 10 of the original actual array A. And this could be an issue, potentially, depending on how clever the compiler thinks it's being. When it's doing this, it could maybe start to reorder these. For example, it might say, okay, well, doing this is faster for some reason, or doing this is, for some reason, I want to do this before I do this. As far as the code here is written, that looks fine, because these two, as they're written inside the subroutine, they look like completely different things, completely different independent operations. But because of the way that we've called it here, they actually aren't. And now that means that the order here does matter. Perhaps we were intending to do this, perhaps we weren't. but this becomes a little bit dangerous because of this. So what we really should try to do to prevent any issues where these two names inside the subroutine, inside the procedure, actually refer to the same locations in memory, is to try to write procedures which only have a single intent in out. Because these were both intent in out, we're opening ourselves up to issues if the compiler decides to swap these around or make other optimizations. Optimizations which would be perfectly fine if these really are different things, but in this case they aren't. So that could be an issue. Also, imagine this. Imagine we have a module, and that contains, in this case, subroutine my subroutine. The module contains iHost, and that's an allocatable array, and it's public. So anything using my module is allowed to grab hold of iHost, allocate it, deallocate it, do whatever with it, and indeed pass it through as an actual argument to any procedure. The subroutine, my subroutine, has iarg, and that's expected to be an integer allocatable intent in out array, iarg, rank 1. Inside that, it's probably going to start doing things with iarg, and it's probably going to start and it's also perfectly allowed to start doing things with iHost because they're in the same module. The problem: what if we called in our program or wherever else we were calling my subroutine from? What if we did call my subroutine iHost, which we've also got from the module? So now inside the subroutine, we could be doing things with iHost, as it is here, and iarg, which is also iHost. That's again probably going to do some strange things that we weren't planning for, and that, depending on optimizations, could become even worse. This is, I'd say, a little bit easier to avoid because we in general say things like this. This is essentially at this point a global variable, and it's just better to avoid this in general. This is one big reason, but there are several. So by if you can avoid module scope data, don't include any data up here, which is intended to be used elsewhere, and just keep everything inside the procedures and use your functions and subroutines to control that flow of data. That should prevent anything strange like this potentially causing issues for you in the future. So we aren't directly talking about pointers here. Under the hood, we are talking about pointers because we're talking about locations in memory being used with multiple names attached to them. But this is more generally sort of being aware of the fact that your names can be reused in this way, in ways that you perhaps aren't intending them to be reused. And that depending on how the compiler interprets that, and depending on what your code is doing, this can cause issues. And you may just, there isn't anything here that the compiler can take a look at and say this isn't correct. You aren't allowed to do this. It could compile fine. It probably will compile fine. There's also a very good chance it would run perfectly fine as well, but there's also a completely non-zero chance that it could go horribly wrong, and you may never even be able to see it going horribly wrong. So these are just two recommendations on this side. If you can, try to write your procedures with just one intent in out. That stops this issue of maybe multiple names within the procedure being aliases for the same memory. And if you can try to avoid module scope data like this, then that avoids a whole host of issues. This is just one of them, as I say, the possibility that you then call a procedure which has it as an actual argument and also as a module scope variable inside itself. As for when coming back to pointers proper, pointers in the Fortran sense, there are some conditions on how you use target in the context of dummy arguments. So if you have a pointer that's associated with an actual argument, then it isn't allowed to become associated with any dummy arguments, and that's because you can then get copy in, copy out happening. And then if a dummy argument has the target attribute, then any pointer associated with it isn't allowed to be associated with it anymore at the point that you return from it. You can imagine this one might cause all sorts of weirdness, all sorts of confusion. Okay, this is a little bit of an aside. This is something we'll be touching on here and there. So I think actually from now on in this course, we'll actually be starting to, in little bits here and there, see more and more object-oriented code creeping in. That's what we're actually really building up to here. We haven't yet managed to see a lot of it, but as today and then Wednesday and Friday go on, we'll see more and more object-oriented stuff coming in. I think here's where we really see the first sort of little peek at it. There's a procedure statement. Remember, I should actually say, perhaps I should have said earlier on, remember that procedure just refers either to a function or a subroutine. But there's a procedure statement that says whatever name comes after is going to be a procedure. And this is kind of like the external attributes, which are, or statements, which you might have used in slightly older style Fortran before modules. If in particular you had if you had a function in another code unit before modules, you probably had to do something like integer external f external to say to the compiler, f external, don't worry about it, it's an integer function, it's just coming from somewhere else. That's kind of the same thing that's happening here. Here we're saying f external is a procedure of some kind. We aren't saying anything about it. The brackets say that there's nothing about an interface that we can say about it. It's just, we're just saying to the compiler, it's a procedure of some kind, it's somewhere else. Trust me that when it comes to link time, that name will be there for you to link. It's a little bit sort of just you just have to ask it to trust you and believe you, otherwise things will go wrong. If your procedure is actually specifically a function, then inside those brackets you can give it a type, and that's just the same as doing integer comma external. So procedure brackets integer f external is saying somewhere else there is a function called f external which returns an integer type. Generally, it looks more like this. procedure, and then inside the optional brackets, you can give it an interface spec, so you can tell it specifically about the interface you want it to use, and you can then give it more attributes of its own if you want, and then you just declare whichever list of procedures you're talking about. As for what those attributes are, that's what we're going on to right here, and why we're talking about it in pointers, because what you may want is a pointer to a procedure rather than just an integer or whichever variable type. So what you could have is something like this. So let's say that there's an interface, and here we have it explicitly, and this is where you do need to do it. This is called a specific interface, where we've given it a name and said exactly what it is going to be taking in as its dummies, and if it's a function, what its result type is going to be. So we've said interface, and it's got to be to a function called my external function. It takes a single scalar real x, which is in tens hin, and its result is a scalar real called y, and that's all that has to go into the interface. Then we can create a pointer to that function by saying procedure my external function, comma pointer f. So we're saying it's a pointer to a function with this interface, and it actually points to that function itself. So the name that you give in the interface, this here, has to match the interface here. So there's a little bit of redundancy going on here. There is a reason for that. We will see that as we go on throughout this course. We can also define an abstract one. Again, we'll talk a little bit more about this. Let's say that we've got an abstract interface to some function called if function. Again, real intent in is its dummy argument x, and it returns a scalar real called y. Just end function, if function, end interface. And then if you want, you can create a procedure definition like this, a specific one. You can say that my external function is an implementation of this abstract interface. So our if function, this doesn't have to actually exist as a function. If function here doesn't actually have to exist anywhere. We're just saying this is how a function like this would work. It would take a real intent in scalar and return a real y as its output. And then what we're saying here is that procedure if function is implemented by the actual real function, which really does exist in code, which we have written my external function. And then if we wanted, we could then have a pointer to it. This does seem like a lot of work. Again, a lot of this becomes more powerful in an object-oriented context. But you can also imagine, perhaps, if you've got a whole host of my external functions, which all take in the same argument x and pass back the same real y as its result, they maybe just do the same thing in different ways. You know, they're just different ways of doing the same work. Then rather than write out this whole interface over and over and over again for each new one, my external function 1, my external function 2, my external function so on and so on, doing the same few lines every time, just changing a number here, just define the abstract one once, and then say that each of these is an actual implementation of it. So procedure if function my external function 1, my external function 2, my external function 3, and that's it, done. So we've got a little bit of an exercise just now. It's 14:34 is the time, just gone 2:30. So let's spend 10 minutes doing this. So there's a program in example 2 that comes along with a function in external .f90, which actually looks a little bit like these up here, except it's working with an integer array and returns just its size. And then there's a program, that program example 2.f90 makes a simple procedure declaration to use that to reference it. So there are some problems with that. So so it says here, for example, what happens if you provide an actual argument which is a rank 2 array? It was expecting a rank 1 array. So what happens if we change that to a rank 2 array? So try to change that by now providing a specific interface, so a specific interface block. So like the one, so like this. So this is a specific interface. So try and write one of those for the function. Declare it as a procedure, and then also try using a pointer for that, and then check that it works and see if it is now able to trap errors. So this is just an example of why interfaces are useful in general as well. Without an interface, again, you're just telling the compiler, trust me, it works, it's fine. With the interface, you're actually telling the compiler as it rolls through each translation unit, this is how it should work. And then if any calls aren't correct, they should be caught. So I'll just give everyone, let's just spend 10 minutes on this. I'll give you 5 minutes just to work on it, and then I will start to work on it as well in my window. Okay, good luck, and I'll start chatting again in 5-ish minutes. Hi everyone. I hope you've been able to look at the code and do some of that. Just a quick mention. So I've just changed example 2 very slightly so that it now tries to call array size. Oops, I haven't actually. To call array size on a new array B, which is rank 2. And I can compile that perfectly fine. And if I try to run it, I get a size of 0. So it's plainly not actually working. And that's because the array size function actually only takes a rank 1 array in. So when B is carried over to it, it now thinks it's working with a rank 1 array, and it gets very confused and gives us an incorrect answer. So there's plainly, room for improvements here. That shouldn't have been possible, but it was, because we said it's a procedure integer, which is the same thing as integer external. We're saying compile it. Don't worry, trust us that what we've done here is correct, even if it isn't. There's a question in the chat. Can a procedure statement and an abstract interface be used to define the type of an argument to a subroutine instead of declaring it as its return type with external? The procedure can't, but the interface can. Yes, so you can use so the procedure, you would always probably you would have nothing inside. What am I saying? Procedure might sound, but the type of an argument. So the types of the arguments, I should go back. Yeah, the types of the arguments to a subroutine specifically, not a function, a subroutine, would just go in the interface block here. So you would just say subroutine whatever, subroutine whatever the name of your subroutine is, open bracket, dummy arguments list, close bracket, and then in here you would specify what your dummies are and their intents, and then you would do the same with an abstract one. All you're saying is there are subroutines out there. I'm not going to say what their names are, but there are subroutines out there which take in this list of dummy arguments, and it says nothing about how they're implemented. And then when it comes to the procedure, at that point, what you're doing is you're saying there are now I'm now telling the compiler specifically that there is a subroutine of this name out there, which is an instantiation, I guess, is an implementation of that abstract interface. So it's no longer abstract. We're saying there is a concrete bit of code out there which actually does this interface, which actually has the cool signature of this interface that was previously just abstract, but now we're saying is a real one. So really, external, we would try actually really not to use in modern Fortran. We would try to not use it if there were any reason not to, and really there shouldn't be any reason to use it. A mixture of interfaces and procedure statements does everything that old external statements did, but much better. And that's basically what we're seeing in this this example. I hope I understood your question. Yes, so there are issues going on in the code. So let's take a look. So real dimension. So oops. So let's go back. So this is what we had originally. I think. Size of A is 0. Let's just try to fix it straight away. So there are issues with it. Let's try to put in that interface, and what we'll do is we'll see if the compiler is then able to help us, because this is where these this by itself is an issue just waiting to happen. So let's start off. Let's start off by, what was the first thing to do? So let's write a specific interface for it. Okay. That means going up here. So interface, and then let's just end that interface. And we're going to say that it's a function. We can basically copy what we have over here on the left-hand side pretty much. We can just use that as a reference. So we're going to say it's a function. It's called array size, and it takes in a variable called a. The names here don't actually matter too much. What matters really is their order and their type. And it returns I size. And then in here, we'll say what those actually mean. So what is A? Well, we can just again see on the left-hand side, A is real, its dimension is rank 1, assumes shape, and its intent in. It's never going to be changed by anything in the code itself. That's A. And then, of course, I size. What is I size? It's like that. And then what we can do is we can say the procedure array size. Let's just change this and make this array size itself. So we're saying now that we have an external function called array size, which uses the interface also array size. I've got an extra R in there. So let's save that like so, like so, and then try to compile. Oops, I missed output end function in there. Okay, let's build that. Oops, duplicate external. Did I not delete the other one? Array size, procedure array size. Oh, I've done, yeah. Oops. Yeah, so, yes. Compile line. Oh, it's just an integer. No, why is it? Have I missed something silly here? I think I'm just going to keep this as array size. Yeah, oh, of course, because then we don't need this. Let's just delete this. This is right. Of course, I'm being silly. We don't actually need that. So now we've actually told it how to do that. So keeping that procedure line was the issue. And now that works. So now that actually understands how it should be calling it. So the use of that array was an issue when we were just saying it's external, but we aren't going to bother to tell you at all about the interface. F90, keep that open. Okay, so that's that. Sorry, I think. Oh yes, I think my question. I have this subroutine in my code. So say I have this subroutine in my code which takes in a function func to then call and use the result, because I replace this use of external with a procedure and an abstract interface. Subroutine first 0, list of arguments, implicit non-integers in external func. Yes, basically yes. That would be the correct modern in inverted commas way to do it. You wouldn't even need to be need it to be abstract. You can just provide an interface as is, and abstract is really only useful in this context for when you're expecting to be working with a long list of functions or subroutines which have the same interface as one another. So they have the same argument list or return type if they're functions. Otherwise, if you're just doing one specific one, there's no real advantage to doing it with an abstract interface. You would just write a specific one like this. Okay, so I think that's that. The next thing to do was to so I hope I've answered your question, Ian. If not, please put in chat and I'll come back to that. But moving on just with this, so we've got this, but now let's try to make it into, okay, brilliant, perfect, cheers. Glad to be of help. Let's try and instead change it to be a pointer to this. So let's now say that rather than just using that interface, we're going to use a pointer to it as well. So we can say procedure. So when we say procedure array size, we're kind of almost invoking the interface as a variable kind. It's sort of that way of thinking, kind of. And let's just call it pointer PF, pointer to a function. Well, pointer to function, and that points to array size. And what we should now be able to do is add down here print star PF A. Unless I've again missed anything silly, like I did before. That's hopefully all good. Yep, perfect. So you can see now we can use it two ways. We can use array size directly using only the interface block, or we can use PF, which we said is a pointer to a procedure like array size. Was there anything else? I think that's that. Okay. Last thing to check. Let's try to break it in the same way as I did before. Let's create B224, a new rank 2 array, and let's also print star. We can use either of these. Let's just do PF B for the sake of it. So we're now trying to call this incorrectly. We said up here in our interface, it takes a rank 1 input array A, and here we've tried to call it on a rank 2 array B. Let's see what the compiler says. Rank mismatch rank 1 and rank 2. So this is now not compiling. Remember, anything we can do to help the compiler spot issues is a good thing. We want our compilation to fail if there's a reason for it to. The sooner we can see that something isn't right, the more likely it is that we'll have an opportunity to fix it before it becomes a problem and we don't even realize that it's happening. It helps us prevent bugs from ever becoming a problem. Okay. Okay, here's what we'll do now. We've been going, it's just about 3 o'clock. It's about 5 minutes to. Let's take a break until say 10 past 3, and then what we'll do in the meantime is anyone who wants to can have a quick go at this challenge, maybe during the break. When we come back from the break at 10 past 3, I'll quickly go over this, and then we'll move on to the final session for the day, which is on derived types. So let's just finish there just for a little bit. Let's just come back at it's about 13-14 minutes now. Take a very quick break, and start again at 10 past 3. Okay, see you in just a wee bit. Okay, welcome back everyone. Hope you've got to stretch your legs. Okay, so I think everyone is here, so we'll just be moving on with the final session of today. We'll aim to finish for 4 o'clock. Just have a question. I actually should have mentioned earlier on. Yes, this is being recorded, and there will be links going out to everyone. So I would imagine that this will be that recordings of this will be available to everyone early next week, I would hope. I think we ask. I think we asked that those links aren't made public, but for your own use, yes, you can come back and watch the videos of these sessions as many times as you like. So just in case anyone has to miss any of the sessions. Okay, so I said if anyone wanted to have a quick go at this over the break, you are welcome to. I'll just quickly show how this works now. So ask this final challenge of this episode to see if we can make the same thing work again with an abstract interface. So I've just gone ahead and made the changes here. So before we had an interface to array size. All I've done is I've added the word abstract here, and I've changed the name of the function of this now abstract function. Before it was array size. I've just made it my array size because those names have to be different. They have to be different from one another. Otherwise, we have both an abstract function interface called array size and a specific interface called array size. And of course, those names collide with each other. So I've just made this my array size, but the actual contents of the interface, so its list of arguments, just that one A, and its result are the same. And then down below, all I've said is that I'm now making the specific procedure array size use the abstract interface, my array size. And I've also used my array size as the interface for pointers. So this line is actually just slightly of interest here, that the pointer itself is pointing to array size, it's pointing to this interface, but it is itself using my array size. It's still using the abstract. This doesn't actually matter too much here. We could have done this and just had it point to array size. But what matters is that the pointer is being pointed to use an interface of this specific kind, and we are now initializing it to specifically point at the array size function, and then that just builds like so and works just as before. Before we move on, are there any quick questions about that? If anyone had to go and run into any issues or just has questions in general about the abstract interface question or pointers in general? Otherwise, we will be moving on to derived types. Okay, brilliant. Let's carry on then. So derived types. So I imagine probably most of you will have used these in some way, but this is within the course. This is, as I say, we really start to push on towards object-oriented programming. And that means that we really need to make sure we're up to speed with types. So if you want to go the full, very formal definition of what a type declaration looks like, it's what we have here. Type, square bracket, attribute list, and so on. It's probably easier to just look at what we have in an example. But I will notice that a contains part, if we have a contains section, and this is optional, this is where we can actually put we can put procedures inside our types, and these then become type bound procedures, which are essentially class methods in other languages. So what we'll start off with is just by thinking about how we can encapsulate data. That means bringing in the public and private statements and attributes to control which data is visible from what code from within this type. So if we want to make an opaque type, that means that we can use the type, but we can't get at the data that's inside it. We would have to set it up like this. So we will just call our derived type my opaque t, and we'll say, okay, type, comma, public. So that means that we are allowed to now declare variables of type my opaque t. Then inside it, we put private integer data, idata. So we can use the type, but if we try to access idata inside of it, if we create one of these, will be told off. The compiler will tell us, sorry, you aren't allowed to do that. iData it will either say iData doesn't exist, or iData is private, something along those lines, depending on which compiler you are using. You can also mix that up if you like, so you can have a semi-opaque type. Let's call that my semi-opaque T. Again, we say that the type itself is public. It's available for whoever wants to use it. Inside, we say everything is by default private. Integer iData. So this goes with that default state of being private, but then we override that for ndata, which is also an integer. We put comma public, and that overrides the private here and makes that public again. So from outside the module, which we have hopefully defined this type in, that should be how we're doing things now. We can create my semi-opaque T's, and we can access and work with ndata. iData is hidden from us. The only code which would be able to access the iData of this type would be other procedures in the same module as it. If we want to access and use those components, we'd use the percentage sign. And of course, the components of any type could themselves be derived types. And this leads to what we call an ultimate component. So an ultimate component is basically an intrinsic type. So once you so if you have derived types built up of derived types built up of other derived types, and you can sort of walk back through them by applying percentage sign after percentage sign, at some point you would have to reach the ultimate components, which are the intrinsic integers and reals and characters and so on. Things for which you can't apply the percentage sign anymore. It's worth, just as a very, very quick aside, noting that as well as public and private, there is also a protected attribute. We will talk about it later on, so we're setting it as an aside for now. But it's worth noting that if you're used to protected from C++, for example, it doesn't mean quite the same thing. There's also a little bit of controversy over whether it should actually be used, even though it is in the language, because it does sort of allow sort of slight sidestepping of encapsulation, which if you are trying to write proper object-oriented code, it is a breakdown of that paradigm. So you may not want to use it anyway, but there is that possibility there. As I say, we'll cover that later on when we talk about sub modules. How do we get values into our derived types? So for a transparent type, it's very simple. So if everything is public, then we can not worry about anything at all. We can just say create two my transparent types. Everything is public. We can access the type itself, and we can also access everything inside it. We'll create one called A and one called B. Then what we can do is we can just say B equals my transparent type. So we just use the name of the type itself, open bracket, and then we can provide the values in order here to go into the two components. So this is assuming that you've got something like this, iData and ndata, except everything is public. So 2 would go into iData, 3 would go into ndata, and that would be it. And we could also then do a further copy of that into A. So A equals B means that it would then go through each of the components of B and put the same value into the same component of A. And it rolls through. So if any type component is itself a derived type, it will just do the exact same thing. It will roll through as far as it can, copying the values of each component as it goes into the correct place into the left hand side symbol of the equal sign. If we are actually working with any private components, such as in the my semi-opaque type or the opaque type that we had up at the very top, then we need to do things a little bit differently, because remember, in this case up at the top, this wouldn't work, because now the things inside these are actually hidden. So any code outside the module or the code unit where my semi-opaque type is defined, they aren't able to access those private components. They have no visibility on them and no ability to change them. So what you have to do is you have to write an initializing function to go with it, and you can see we're really talking about object-oriented type thinking here. Now we're talking about initialization. So you'd write a function. It's probably got a similar name. So if we had my semi-opaque underscore t, we'd maybe just write a function called my semi-opaque that takes in the two values which we want to put in it, idata and ndata. They're both intent in. Just the same types as in the type itself, the my semi-opaque t type, and the result, we'll just call it, is of that type. And then we just say res idata, res ndata equals idata and ndata. And then you just call that like this. So type my semi-opaque underscore t, a, and b. You can just do this, my semi-opaque 2, 3. And then you can just do a equals b. This second line, this works because a is again in the same code unit as b, if you like, because they're both defined through this type. So that means that they do actually have visibility on each other's components. It's not like this first line where we're calling this from outside. So a very quick exercise here. We've got an accompanying module, my semi-opaque type T. And that has a public definition of the type we had above, and also a function to initialize it. Let's take a quick look at that. Let's go down into 4. So let's take a look quickly. My semi-opaque type .f90. Here it is. So as I say, it's inside a module, which is exactly how we should be doing this. We define a module, implicit none. So everything in here is public. Sure, that's the default setting here. Type public, my semi-opaque underscore t. But then inside the type, we make everything private by default. That applies to idata. However, for ndata, we override it to public. So we've also got this function, my semi-opaque. This is exactly what we talked about just a second ago. So let's take a look at the other codes here. Example 1.f90, which we use along with it. And that uses the same module, my semi-opaque type, creates my semi-opaque t's a and b. Says b is going to be equal to my semi-opaque 2, 3, a equals b, and then it also calls a function which we haven't written yet, which is our first task, what we're going to do just here, to just check that that's actually worked. So let's just spend, it says 5 minutes here. I feel that's a little bit too much. I think this is hopefully pretty simple. Let's just see if you're able to write down here, I'll just go right down here, a new subroutine called my semi-opaque print. What does it do? Oops, subroutine, and I'll let everyone get along with this, and we'll just come back to it in a few minutes and see if what I do matches what all of you have been doing. That's just, yeah, two or 3 minutes, I think, is all we need here, and then we'll chat about it. Okay, I don't think this is too tough, so let's just quickly see what I'm going to do and check that it matches what you've done. So we know that we had 2 arguments to add, and we're just going to be printing out these components. That's all we've been asked to do. Check that the components for both A and B are correct after we've been doing this assignment. So let's add in, let's call it name and variable for the sake of it. And we want the first one to be character, and we'll make it len equals star just to be simple. Make them both intent in, and name, and then our var is going to be a type of the same type we have above, my semi-opaque t, and that's also going to be intent in, and we called that var for variable. And then very, very simply, all we need to do is print star what these are. So let's say name. I won't bother with any formatting to make it look nice. Percentage, and the first one was idata equals, and then var percentage idata. Print star name and end data, this one is now, equals, and I've made a slight typo, var percentage end data. That's hopefully enough. So we, on the left hand side, are creating B and using the my semi-opaque function to fill out its fields, its components, and then we're saying A is equal to B, and then we're using our new semi-opaque print subroutine to print out the components within it. So let's give that a go. So let's ftn my semi-opaque type t, and example was it 1? Example 1.f90, which compiles, which is a nice start. 2 and 3. So I hope everyone was able to manage something similar to that. Just to be really clear why this is okay, because the subroutine my semi-opaque print and the function my semi-opaque are in the same module as my semi-opaque t, they have the ability to see and change n data. I data. So I data is private. So inside example 1.f90, we can, if we want, we can do things with a percentage n data because that's public, but we can't do anything with I data. I data is private inside the type, and that means that only things inside the module itself are able to do anything at all with it. And that's why the function and the subroutine can both use idata. Okay, I hope that's okay for everyone. As ever, please put something in the chat if you aren't sure about any of this, or want me to go back over something in more detail, or whatever helps you. Okay, carrying on to allocatable components now. So we can put anything we like inside our derived types, and that includes allocatable arrays. So let's imagine now that inside our array type, we will call it myArrayT. We have an integer nlen. This is probably going to say how many values are going into our array, and then real allocatable array called values, which is rank 1. So your intrinsic assignment works really very similarly, but there are some extra things involved. So the first thing is that if the values component of A on the left-hand side here is already allocated, then it will first be allocated and then reallocated depending on the size and bounds of the values inside B. So basically step 1 is to wipe values away from A, and then to set it up again to match the size and bounds of values in B, and then finally we copy all of the values that are in B's copy of values into A's copy of values. If at the point of this copy the values array inside B is actually unallocated, then if the one in A was actually allocated, it will be deallocated and then just left that way. So whatever values was in A to begin with, it will be wiped if necessary, deallocated, and then it will be reallocated if necessary and copied into such that it matches whatever was in B. And I think particularly if you've come across this before in other languages, you might be aware of things like deep and shallow copies. And this is a deep copy. So when we do this, we aren't leaving anything to tie the memory of A and B together. So everything that was in B gets a new copy of it made specifically for A when we do this. And just as before, if these allocatable components are themselves maybe of derived types, it will move through all of those and deallocate and reallocate as required until we finally reach any ultimate allocatable components. And just as before, so we saw in the previous, we saw earlier on today that if you have an allocatable array that you pass as a dummy argument through to some procedure and you give it intent out, then at the point when you enter that procedure, the array will be deallocated at the point of entry. And this is just the same when you have a derived type which contains allocatable components, and that derived type is an intent out argument. So if you were to pass my array T through to some procedure and say, yep, it's intent out, at the point you enter that procedure, values, even if it was already allocated, will now be deallocated. There's a question in the chat: is there a performance impact when using those derived types that do a lot of dealloc and alloc calls? I mean, yes, there will be. It can be better to try and avoid that if you can, and we will actually see a little way around it right away. So in some ways you would want to try to avoid doing this if you can, particularly if those allocations are really big. Most of the time, and I mean this is true for everything really, if you can set up your allocations once and once only and have them last as long as possible, that's probably always going to be the best thing. If you want to, yeah, definitely try and avoid doing this, you know, millions and millions of time. Yes, so yes, some codes, the comment, some codes grow arrays and so realloc. Very true. What you may want to do, and it's less efficient for memory, but probably more efficient for just runtime, for actual wall clock performance, I guess, is to maybe allocate them bigger than you need in the first place. So in some ways, a really old style Fortran code where you would just say, I'm going to create an array of size n max equals 20 billion, but only use n equals 10,000 or whatever, is actually in some ways a little bit more performance. But yeah, definitely, if you can avoid that, better to do that. It just needs a little more work from you. This is why I think people in C++ spend a lot of time working on their own, you know, specialized memory allocators. It's a lot of work, but if you can do it well, it can get you extra speed. So one way around that can be to do a shallow copy, and that's basically if you use pointers instead. So although pointers and arrays are very closely related, the behavior in Fortran is actually different. So we've got type public myArray pointer type, pointer t, contains integer nlen, and a real pointer. And this now here is a pointer to an array. Remember, this isn't, I'm going to keep on saying this because it is strange. This isn't an array of pointers. This is a pointer to an array. So we've got a real pointer, a real array pointer called values. When we assign this here, that now means that the pointer becomes associated with the target on the right hand side. So b nlen, let's say we've got these two myArray pointer t's again, a and b. Let's say that b nlen is equal to 10, and then we allocate b values with size b nlen. What that does is it says, let's allocate a real array of size b nlen, and the values pointer is now going to point to it. So we've created an array on the heap, and values b values points to it. When we do a equals b, we no longer do this whole thing that we did before. We do not do this. We don't deallocate, reallocate, and everything. Instead, we very simply just say that the a values pointer now is point to b values. So the pointer in A points to the same chunk of memory that we just associated. So we just allocated for B. And that can be good for performance because then we stop doing this deallocation and reallocation. That this can save us performance if we're expecting to do this a lot for whatever reason our code needs. But as always, now we're working a little bit closer to the raw memory again. We need to be a little bit careful at the same time, because what happens now is if B goes away and deallocates its values for whatever reason, A was still pointing there. So the A values would then at this point be pointing to memory that has been allocated. It wouldn't be in a good state. You wouldn't be able to use it safely at all anymore, possibly at all. So yeah, it's just something to be aware of. It can give you performance, but whenever you're working that little bit closer to memory, just bear in mind what memory is being allocated, what memory is being allocated. Yeah, and just to restate, this in contrast to the deep copy is a shallow copy. So we do actually copy the value of n-len, but the pointer value, the pointer array is not copied. We just point the different pointers to the same spot in memory. Okay, we have another quick example, which nearly brings us up to the end. So we have a module now in my array type.f90, which gives us both of those types above, along with a function to initialize array values. So let's try to compile it, check the values printed out, and then see what happens if we insert the call to my array destroy.a. So I'll just start things off, and then I'll let you have a quick go yourselves at trying out these changes. So let's just quickly see what happens. So taking a look again, we've got my array type.f90, and here's what we have: my array t and my array pointer t. In one of them, we have a real allocatable array called values, and in the other one we have a real pointer to an array, also called values. So really these are very similar, but not quite the same. And then we have my array allocate, which takes in my array t, and my array destroy, which also takes my array t. What does my array allocate do? It just puts some numbers into a my array t. My array destroy does the right thing to do. We're doing some cleanup here. Sets a n-len to 0, and it deallocates whatever was in the values array. Let's take a look inside example 2.f90. Oops. Ooh, gone all wrong. I wasn't. You split example 2. Example 2.f90. There we go. Inside example 2, we create a myArray t target called A, a myArray t called B, and a myArray pointer t called C. We set up B and allocate it. So we fill it with values, and then we set A is also equal to B. Check the state of A. And then we're going to set up C, and we're going to say that C's n-len is equal to A n-len, and we point C values to A values. Then let's check the state of C. So let's just try to compile that and see what happens. So ftn my array type.f90 and example2.f90. Okay, /a.out. State of A has a size of 3 and it's allocated true. State of C, 3, true, 1, 2, 3. Let's just check again that that's what we were expecting. And we were checking, yes, is A, how long is A? Is the values allocated? What is the length of C? And is the pointer in it associated? Yes, it is. And we also got the values that it was pointing to. So you can see here that that is working. This is all working correctly at the moment. So our question, what happens if you insert a call to my array destroy A and then try to print everything out again? So let's just do it. Let's just find out. So let's put in my array destroy A, and then let's just print out the state of C once more, and let's try to compile that. Oops, my array destroy. I do this wrong? Let's open up the of course, it's not a function, it's a subroutine. Okay. Okay, let's try again. So what we get now is a slightly nasty state of affairs, actually. So these are the same two lines we had before. On the third line, we get, okay, state of C, size 3, brilliant. Is the values pointer, is it associated? True? Yes, brilliant. What are the values in it? Garbage values. Actually, this is not good at all. So this is what we said when we meant that it can end up in a bad state. So that data went out and it's been released to the system. So our pointer is still pointing at memory. Fortran still thinks that it's pointing at something meaningful, but because in the meantime something else, in this case a percentage values was deallocated, the actual values at that memory, at that location in memory, they don't mean anything anymore. They aren't safe to use. So this is probably say you need to be a little bit careful at this point when you're doing this. You would really want to have some kind of guards in check, if possible, to help you keep track of the fact that now that this has been deallocated, C is no longer safe to use. You can do that. You can code your way around this, but it's a little bit more overhead and a little bit more effort from you. Okay, I think that's everything. Yes, of course. Yeah, we can. That's something I should show you as well. Yes, we can run that as many times as we like, and we will probably get different values every time. It's interesting that the second one is always 0. I'm not sure why that is, but the other two are changing every time we run because it's just garbage data. Who knows where it's pointing now? Who knows what its meaning is? Okay, very quickly, let's try this. What happens if we try to make a direct assignment between a myArray T on the right-hand side and a myArray pointer T on the left-hand side? Let's just quickly have a go at this and see what happens. So let's go back into example.f90. And oops, example2.f90 would be a good place to start. Okay, so we have a myArray T on the right-hand side. So let's just try and do this instead. Let's do C equals A, very simply. What happens here? It doesn't build. And that's because these are just different types. The compiler doesn't like that the two things are different. So even though one is an array and one is a pointer, and for the most part they kind of look similar, sort of, in the underlying operations that you would do with them at the assembly level, the fact is that as far as Fortran is concerned, they are actually very different things. A pointer is not the same as an array, and they both are in different types. You can't convert between the types like this. You could write functions to do so. We will see a little bit about how to do that tomorrow morning, I think tomorrow morning. But for the time being, you cannot just intrinsically do this. Wednesday morning, yes. Sorry, not tomorrow morning. Wednesday morning. Yes, you are right. Okay. I think we can at least get down to the challenge. I don't think we'll have time to do it today, and we can maybe start off on Wednesday morning with that if people want to have a go at that this evening or tomorrow at some point. But let's take a look at least at a defined assignment. This is actually touching on what I was just saying, actually. So if you need to do assignments of some kind other than using intrinsics, you can do an an overload of the assignment operator equals sign. So if you wanted to say, okay, let's work out how to assign between two objects of my array T, let's assume that we couldn't because there were strange components in there and the compiler couldn't work out how they convert between one on the right-hand side and one on the left-hand side. And what we can do is we can go back to interface again. So interface has so many uses now. It's a very, very helpful bit of code. We can write a new way to do equals, basically. So interface assignment equals, and this is a fairly boilerplate bit of code here. You would always do have this first line and this last line, and then in the middle you say module procedure, whichever functions subroutines actually in this case, sorry, you use to do that assignment. So up in the top of your module, you do interface assignment equals module procedure my assignment, and then down below in the contains part of your module, you then have to tell it how to actually do my assignment. And when you're doing assignment equals, when you're saying how an assignment operation should work, it always looks like this. It's a subroutine. It has two arguments which are both of the same type, and sorry, no, I was saying they are both of one has to be of intent out or in out, which is the left hand side of the equals, and on the right hand side, which is represented here by B, it's intent in. So I think we will actually finish just here for today. What I think we'll do is we can leave this just for now. And if people want to have a go at this in the 5 minutes before 4 o'clock, please go ahead. I will stay online. If you want to have a go at this, as I say, this evening or tomorrow or first thing on Wednesday, please do as well. And when we start on Wednesday, we'll just begin with this little exercise here. We'll just take a look at how to do this. So we couldn't make an assignment between my array pointer T and my array T. So all we want to do is something like this. We want to write essentially my assignment that will do that. It will take in a my array pointer T on the left and a my array T on the right, so A and B in this here, and it will set them correctly up. It will say what do we do to A using B so that A after the end of this subroutine is properly assigned. So yes, I'll leave you to do that now in the last few minutes here before we finish. Otherwise, if you want to have a go, please do at any point you're able before 10 o'clock on Wednesday, and we'll start then by just spending a few minutes looking at this. This is one of those things I think that again looks like it might be a little bit tricky at first, but actually isn't too bad. Otherwise, I hope it's been interesting. I hope it's been maybe useful for you. I hope maybe you've learned some things that you weren't aware of before today. I'll be sticking around, so if you have any questions, please put them in chat or just yell if you want to unmute yourself. Otherwise, I hope you enjoy the rest of the day. Have a good day tomorrow, and I'll see you on Wednesday morning. Thanks, you're very welcome.